let's go through the second class lever again, just because it cut off. So we know the load will be in the middle of this lever arm, and the fulcrum will be on the side, so is the effort on the side. But we could use the example of a deadlift to explain this second class lever. So we know that the load is going to be the body weight and the weight, so the barbell and the body weight of the participant. We also know that the effort is going to be the latissimus dorsi of the back, and the quadriceps of the leg, and the gastrocnemius of the lower leg. The fulcrum, this part here, will be on the balls of the feet. Now we can look into the detail of the third class lever. Now we know on this one that the forces will be in the middle, the load will be on the side, and the fulcrum will be on the side again. So we could use the example of a javelin throw of the arm. We know that the fulcrum will be the elbow over here. And we'll know that the effort will be the biceps and eventually the triceps too. And then we know that the load will be the weight of the javelin that they're throwing. So that's the example of the third class lever. Now we can now have to look into mechanical advantage. So mechanical advantage is the ratio of the force produced by a system to the force applied to it. So now we can look at what this means. So mechanical advantage, it comes into two roles. So there are three main parts to this. There are strength, there are range of motion, and speed of movement. So let's look into those quickly. So strength obviously is the weight lifted, so the load that has to be lifted, and the effort, the muscle that has to lift it. The range of motion, so how big is this range of motion, and how quickly does it need to be done, so the speed of movement. Now we look at the equations for it and what levers would match up with which. So now we can look at if the effort arm is a greater distance than the load arm, this is probably primed towards the strength, less of the range of movement and the speed of movement. So that's typically what a second class lever would be. We go back to our second class lever. We can take this example of a deadlift. It's much more strength based than either of these two. Now, if the load arm is a greater distance to the effort arm, this typically demands a greater range of movement and a greater speed of range of movement, a range of motion and a greater speed of movement. Now, this is typically tailored towards a first and third class lever, as they are not typically designed for strength, but greater ranges of motion and a greater speed of movement. Now, this equation to find the mechanical advantage would be the effort arm length divided by the load arm length. Now, if the effort arm length divided by the load arm length is greater than 1, that means that it is more strength-based, so maybe a second class lever. But if it is less than 1, then it will be tailored towards a movement with a greater range of motion and a speed of movement. Now let's apply this to our examples. So we could use a disadvantage example first. So this disadvantage example is the one that is lower than 1, not greater than 1. So something that was strength-based is going to be an advantage, not a disadvantage. This does not mean it is genuinely a sporting advantage to have it. It just is dependent on whether it is strength or range of movement and speed of movement based. So our disadvantage version would be of this, oddly, would be a second class lever. Usually these things would be more about speed of movement and range of motion. But we can look at this 100-meter sprinter, and we can look at the fulcrum being the ball of the foot, the effort being the gastrocnemius and soleus, and the body weight being the load. And we know as a second class lever that if we go back here, we know that the load is going to be in the middle, and the fulcrum and the effort are going to be on the side. So now we can look at the equation again. So now I know that the effort arm divided by the load arm equals the mechanical efficiency, the mechanical advantage, right? So if it's above 1, it's going to be mechanically an advantage. But if it's below 1, it's going to be a disadvantage. So if we do, our effort arm, we know, is going to be 0.05 meters. And our load arm is probably going to be around 0.18 meters. Okay? Which means that it probably would be, this equals around 0.28. So 0.28, we know that that is smaller than 1, which means that it's more about speed of movement and range of motion. And this can be seen within the runner, that it's all about speed and about range of motion of how far they can get their legs behind. Now, our advantage example, this can be shown through another second class lever, which is more tailored, right, towards an advantage, which is greater than 1. We can look at the deadlift, so that we can see the fulcrum, which equals the ball of the foot. We can look at the load, which is the weights and body weight. So the weights would be the barbell with the weight attached to it, and the effort would be the gastrocnemius and soleus of the inferior part of the leg. Now, if we take this equation again, it would be the effort arm divided by the load arm. Now we know the effort arm here is 0.25. The load arm is 0.15. So now this equation put into play would be 0.25 divided by 0.15, which equals 1.67, which is greater than 1, which means that it's more strength. It is an advantage, especially in this movement, as it is a strength-based movement. Okay, we move on to our last topic, which is torque. So torque, the definition is the measure of the force that can cause an object to move around an axis. So we know that there is an eccentric force that is applied to this discus. We know that so it is not going through the center of mass, because that would not be an eccentric force. Okay. So to find torque, we have to use the equation, the moment of inertia times angular acceleration, as we looked at before. So now we know that this would be around 0.3 times 10.5, which equals 3.15 newtons per meter. Thank you for listening.